Dear students, today our topic is about spin-orbit coupling. So to understand what is the spin-orbit coupling, first we need to define it. So for how we can define the spin-orbit coupling? So it is, we can say that spin-orbit coupling is interaction. It is interaction between electron spin magnetic moment, spin magnetic moment, and proton orbital magnetic field. So what is the spin magnetic moment of electron? So we can write the spin magnetic moment of electron by mu s. So the mu s is equal to minus Es divided by MEC. So this one is the formula for the spin magnetic moment of electron. So the second thing which we need to understand is the proton orbital magnetic field, which can be represented by B. So we need to understand that what is the origin of the spin magnetic moment or proton orbital magnetic field. So how we can understand the proton magnetic field? So what is origin? So what is the origin of proton orbital magnetic field? So in order to understand the proton magnetic field, we can explain it classically. First, let's suppose we consider the proton, that is of charge plus Ze, and so we consider the electron is moving in a circular orbit around the electron or around the proton, positively charged proton. So this one is the electron. It's moving with velocity v, and its charge is minus e, and this one is the radius vector r. So this is the direction of orbital angular momentum. So this is the one point of view, that is when we consider the electron moving around the nucleus, moving around the proton. So the second point of view is that if we consider consider from the rest frame of electron, if we consider from the rest frame of electron, then we consider that electron is here with negative charge, and proton is moving in a circular orbit around the negatively charged electron. So its speed will be the minus v, and this one is the again is radius vector, or this one is the angular momentum direction, and this one is the magnetic field. So this figure represents the electron frame of reference. It represents the electron frame of reference. So now how we can explain the magnetic field of the proton? So for this we need to go to the classical electrodynamics. So from the classical electrodynamics, the field, which is magnetic field experienced by the electron, is equal to, it can be represented by B is equal to minus 1 by C into R cross E. So this is the magnetic field which is experienced by the electron. Further, we can modify the equation and we can write it like B is equal to minus 1 over MEC into P cross E. So this is the cross product. So when we reverse the cross product, P cross E, instead we can write it the minus E cross P. So it will reverse this negative sign. So it will be, B will be equal to 1 over MEC into E cross P. So this field is this field which we find, it is from the classical electrodynamics. Is from the classical electrodynamics. So here the P represents the well-known relation of linear angular momentum and is equal to MEV. M is the mass of electron and V is the velocity. So it represents the linear momentum of electron. And what about E? So this is the E is the field which is generated by the proton Coulombic field. So this one is the field which is generated by proton Coulomb force. So next thing which we need to explain and need to know is about this field. So we can write the electric field equation. So the electric field which is generated by the proton Coulomb force is, it can be written as E of R is equal to E divided by R square into R vector divided by R, and it will be equal to the E R divided by R cube. So this is the electric field equation. This one is the field generated by proton Coulomb force. So next thing is that now we need to go to the general relation, need to explain it generally. So how we can explain it in general way? So in a general way we can say that for all 1 electron atoms, for all 1 electron atom, for all electron atom here means that like the alkali metals, you know that in alkali metals have the 1 valence electron. So it has only 1 valence electron outside the closed shell. So when it has the 1 valence electron outside the closed shell, it means that valence electron will experience the central force. Now what is the central force? Central force is also called as the Coulomb potential. We can write it like the Coulomb potential. So now what is the Coulomb potential of the nucleus? So we can write the Coulomb potential of the nucleus like it will be equal to the V of R is equal to minus E into phi of R. What's this? Is also called as the Coulomb potential. or central force field of the nucleus. So as we know that corresponding electric field, which is equal to E of R, is equal to minus del phi of R. So here when we can put the value of the phi of R, so electric field will be equal to the 1 over E into del V of R. And we can also write it like E of R is equal to 1 over E into R divided by R into dV divided by dr. So the next thing is that now we have calculated the electric field. Now what will the magnetic field of the nucleus in the rest frame of electron? So next we need to calculate the magnetic field. Need to know the magnetic field of nucleus. Magnetic field of this one is the electric field of the nucleus, so correspondingly the magnetic field of the nucleus in the rest frame of electron. So we can write the equation for the magnetic field which is experienced by the electron. So this field is equal to, as we have already written its equation, like B is equal to 1 over MEC into E cross B. So this will be equal to 1 over, we can write it by putting the value of electric field. It will be equal to the E MEC into R dV divided by dr into R cross P. So this is the magnetic field, and by further simplifying we can write it like B will be equal to 1 over E MEC R into dV divided by dr, and so R cross B is equal to L. So R cross B is equal to L, and we know that this is the well-known relation for the orbital angular momentum. So this is the orbital angular momentum. So now we have the equation for the magnetic field, and we have the equation for the spin magnetic moment of the electron. So the next thing which we need to know is the interaction of the electron spin dipole moment with the orbital magnetic field B of the nucleus. So the things which need to know is the interaction between spin dipole moment of electron mu s of electron and orbital magnetic field B of nucleus. So it can be represented by the relation HSO. So H is the Hamiltonian, and subscript SO, it represents the spin orbit interaction. And so this interaction between the spin dipole moment of the electron and orbital magnetic field B of the nucleus can be represented by the relation minus mu s dot B. So now we can put the value of field B field and spin magnetic moment. Now we can further solve it, like value of spin magnetic moment is minus E, so minus sign will be cancelled out. E over me c into S dot B. So next we need to put the value of magnetic field, so we can further modify it. It will be equal to E divided by E MEC ME square into C square, so 1 over R into D V divided by dr, so S dot L. So by further modifying, we can write it like as spin orbit coupling term is equal to 1 over me square into c square r into d v divided by dr s dot L. So this S represents the total spin angular momentum, and L represents the total orbital angular momentum. So this term represents the interaction between the orbital spin dipole magnetic moment and orbital magnetic field B of the nucleus. So what about the interpretation of this dipole spin orbit coupling term? This energy term which is turned out, it is observed that it is twice of the observed value. It is twice of observed spin orbit interaction. So what is the reason for this? So reason for this is that, so what is the reason? So reason for this is that we have calculated it within the rest frame of reference. So we have calculated in the rest frame of electron, and this frame of electron is the non-inertial, which is non-inertial frame of reference. So it is the non-inertial, but we know that for electron it will accelerate while moving in a circular orbit around the nucleus. So in order to correct, so how we can make the correction? So in order to correct, for the correct treatment, we must transform it to the lab frame of reference. So we need to make the transformation to the lab frame. So when we make this transformation to the lab frame, so this transformation involves the relativistic addition to the motion of the electrons. So it will add some relativistic addition to the motion of electron. So when it adds some relativistic addition to the motion of electron, so this is known as Thomas Precession. We can say that these corrections are called as the Thomas Precessions. So when we make the transformations back to the rest frame of the nucleus, this leads to the reduction of the interaction energy. So transformation back to rest frame, it leads to the reduction of spin orbit energy. So what will be the amount of this reduction? So it reduce it by a factor of 2. So we can add these corrections, this factor to the spin orbit coupling. So when we add the factor of 2, then spin orbit energy, it will be equal to 1 divided by 2. Now we add the factor of 1 by 2, me square into c square 1 over r into dv divided by dr into s dot l. So we can say that this is the spin orbit energy. This represents the corrected spin orbit energy. And this factor of 1 by 2, this factor of 1 by 2 is due to the Thomas-Bressian corrections. So this is the general relation for the spin orbit interaction energy, and so now we go to the specific case of hydrogen atom. So we can solve it for specifically for hydrogen atom. So when we solve it specifically for hydrogen atom, we know that for hydrogen atom is potential is equal to minus E square divided by R, and then dV divided by dr, it will be equal to the E square over R square. So when we put the value of d by dr square into the spin orbit interaction term, then the spin orbit interaction for hydrogen atom will be, I can write for hydrogen atom spin orbit interaction energy is equal to E square divided by 2me square into c square into r cube s dot l. So this is the spin orbit interaction energy for hydrogen atom. So we can write it, this is for hydrogen atom. So what we can do in the next step, so now we can use the perturbation theory to calculate the contribution of the spin orbit interaction in hydrogen atoms. So in order to apply the perturbation theory, first we need to write the total Hamiltonian for hydrogen atom. So the total Hamiltonian for hydrogen atom is equal to H is equal to P square divided by 2m minus E square divided by R plus E square over 2m E square C square R cube into S dot L. So this term, which is the combination of the kinetic energy and potential energy, this represents the unperturbed Hamiltonian. So this is the unperturbed Hamiltonian, and this additional term, it represents the spin orbit interaction. So we can say that total Hamiltonian in the hydrogen atom, which is the combination of unperturbed Hamiltonian plus perturbed Hamiltonian. So we can apply the perturbation theory. So for perturbation theory, we need to write this total Hamiltonian. This is the unperturbed term. This is the unperturbed, and this is the perturbation.